Hi, today we're going to explore the amazing world of cloth simulation. Cloth simulation is one of the most complicated parts of simulating realistic objects graphically. Since cloth is very thin and can fold and crease, it is represented as a thin shell material model, a model that is used to represent both cloth and paper, as shown here. While there are multiple types of cloth simulation, the one we will be focusing on here is physical-based modeling. Physical-based modeling represents cloth models as triangular grids with vertices of finite mass, like in the mass spring model, shown here.
Let's overview the model we'll be using for cloth simulation, the mass spring model. First, some vocabulary. When simulating physical objects, solids can be divided into two categories. Rigid bodies have a fixed structure, while soft bodies have a structure that can be deformed by forces. Examples of soft bodies include jello, hair, and cloth. Soft body dynamics can be simulated using the mass spring model, where objects are represented by numerous point masses connected by weightless springs. When a force is applied to one point mass, its resulting motion impacts all connected masses, simulating object deformation. The movement for each point mass can be calculated using physics equations governing motion and spring action. In the mass spring model, cloth is represented by a grid of point masses and springs. To simulate a given cloth, first divide the cloth into a grid of equally spaced vertices, with each vertex having a mass of m. Each vertex represents a small weighted area of the cloth. To simulate the structure of the cloth, add structural springs between adjacent pairs of vertices, forming a grid-like pattern. With only structural springs, the square faces of the cloth may collapse on themselves. So to prevent this, add diagonal shear springs between vertices, creating a triangular pattern. Finally, we apply forces to each vertex and calculate the resulting motion. This includes each of 8 spring forces, as well as any additional forces like gravity or wind. One benefit of this model is its vertex-centric approach. The cloth can be represented by an array of vertices, where each vertex stores its own position, velocity, and forces. Force calculations are performed vertex by vertex. The position vector is then used to render the faces of the cloth as a mesh. The force and velocity vectors are needed to help calculate the next position vector, helping animate the cloth over time. When all this is done, the final simulation could look something like this.
Now let's take a look at the equation behind this model. As mentioned earlier, it deconstructs the cloth into independent points connected by springs. Now for some physics. Here, F is the force applied to any single point mass. There are 4 main terms in this equation. Each represents a force acting on the point. The first 3 are environmental forces outside the spring. So first we have mg, which is mass times the gravitational constant, and this is just the force of gravity on the point. The next term is wind, and the last one is air resistance. And air resistance is what is behind fabric swish effect. We can see that if we set it to be too low, the cloth flaps unrealistically, but if it's too high, there's too much dampening. Moving on, the last piece of the equation represents the forces from the springs. It keeps the cloth connected and simulates stretch. Notice the summation. This adds together the forces from each spring, represented by the equation inside. There are 2 main parameters here, k, the spring constant, and x, the displacement. The springs that the model uses can be both compressed and stretched, and they have a natural resting position that they tend to return to. This is x naught, or equilibrium, with the lowest potential energy. The return to equilibrium is caused by the spring force. Remember that forces have direction. This is always opposite to how the spring is stretched, or the displacement, represented by x minus x naught. So displacement affects the spring force. The higher it is, or the more a piece of cloth stretches, the higher the force that pulls it back. The other parameter is k, the spring constant. This represents the stiffness of the spring, and if it's higher, there is a large force for even small movement, and this makes the spring harder to stretch, and translates into a stiffer fabric. If not careful, the total energy becomes so high that the cloth explodes, or the cloth will look like a stiff board. However, if K is too low, the cloth will resemble shapeless jello. While this model helps simplify cloth simulations, its main faults are the explosivity and the fact that K must be set manually. Getting it right is difficult.
Talk about integrators for cloth movement, which help actually animate the cloth simulation. After we pick the cloth model we're using, we must integrate the equations of motion to animate this fabric. Since each vertex within the cloth model has a position and velocity at each time step, We can use the equations of motion from physics to calculate the acceleration of each vertex as well as its position and velocity at the next time step. This specific method shown here is called Euler's method, and it's the simplest method to make for an integrator. However, Euler's method does have a tendency to over-exaggerate movement, so it's not the best integrator to use, and there are many better ones out there.
When simulating cloth, it has a tendency to clip in areas where it folds over itself. You can see here that the cloth on the right is flatter and has a lot of self-intersection, whereas the cloth on the left is much more realistic looking. To prevent this, we can constrain vertices of the cloth geometry to make sure they don't collide. In this example, you can see the model intersecting itself where vertices A and B are sufficiently close together. A naive implementation of constraining vertices would be to compare each vertex to every other vertex when checking for self-collisions. However, this requires a lot of computation. A better implementation would be to compare each vertex to its spatial neighbors by using spatial hashing. This method sorts vertices into buckets based on their 3D position and only compares them to vertices in the same bucket. By preventing self-collisions, the final cloth simulation is less likely to have clipping and looks much more realistic. Basic cloth simulation depicts cloth as a paper-thin, lightweight surface. In order to realistically simulate different kinds of cloth, we need to model both thickness and weight. To simulate cloth thickness, we can use marching cubes. In order to do this, we first construct a surface parallel to the original cloth, shown here by the differently colored surfaces. We then connect their vertices to create a thicker surface. As you can see, the resulting cloth model is significantly thicker than the original.
Now that we've given you the tools to make a cloth simulation, you're well on your way to creating realistic-looking cloth that'll blow you away.